Hello, my awe-inspiring Algebra 1 students. Let's have another summer adventure together. Today, we will factor the greatest common factor, the difference of two squares, and perfect square trinomials. And when we are finding the greatest common factor, we look at the numerical coefficients first to find the greatest common factor of the numerical coefficients. Then we find the greatest common factor of the variables, and it's going to be the variable with the lowest power, the lowest exponent. So our first problem here, we're going to find the greatest common factor of the group of monomials that you see here. The coefficients are 14, 21, 35. Numerical coefficients. So what we're going to do, we're going to factor these numerical coefficients into their prime factors. 14, 7 times 2, 21, 7 times 3, 35, 7 times 5. So the greatest common factor for the numerical coefficients will be 7. When you look at the variables, the variable with the smallest exponent is a 2. So the greatest common factor for the variable will be the variable with the lowest power. So it's going to be x squared. And the same thing here for the y variables. The lowest power is understood to be a 1. So the greatest common factor for the y variable is y. And when we put all of this together, then the greatest common factor for these three monomials will be 7x squared y. And then I'm going to change the problem. I'm going to put plus signs where the commas were, and I'm going to say factor out the greatest common factor. When I factor out the greatest common factor, which is a 7x squared y, what I'm really doing, I'm dividing each one of these terms by this greatest common factor to get what's inside of the parentheses. So let's look at that. 14 x to the fifth, y to the sixth divided by 7x squared y. 7 will go into 14 twice. X squared will go into x to the fifth, x to the third. Remember that when we are dividing like bases, we subtract the bottom exponent from the top. 5 minus 2, 3. And this will be 6 minus 1, understood to be 5. So we have here 2x cubed y to the fifth. 7 will go into 21, 3. X squared will go into x to the ninth, x to the seventh. Y will go into y once. You see the y's cancel out, so we're just left with a 1. When we multiply these, we get 3x to the 7th, 7 to the 35, 5. X squared will go into x squared once, that crosses out, we're left with the 1. Y squared, y to the fourth divided by y to the first is y to the third. When we multiply, we get 5y to the third. And that's how we got what was inside of the parentheses here. And remember that you can go back and double check this by using our distributive property by multiplying each term inside the parentheses by what is on the outside. 7 times 2, 14, x to the second times x to the third is x to the fifth, because when we're multiplying like bases, we add the exponents. Y to the first times y to the fifth gives us y to the sixth. And again, that's another way that you can check this. Next, we're going to look at numbers that are perfect squares. 1, 4, 9, 16, 25, 36. These are all perfect squares. And the way I got these perfect squares, I took each number and squared it. So I did a few more of these. 49, 64, 81, 100, 121, 144, 169, and so on. These are all perfect squares. And again, I got them by taking this number and squaring it. I did some variables also. If I take the x and square it, I get x squared. So the variable x squared is a perfect square. I took the variable m and squared it, and I got m squared as a perfect square. I took y squared and squared, so y to the fourth is a perfect square. I took a to the third, I squared it, and I got a to the sixth. Remember, a power being raised to a power, we multiply the exponents. We're going to look at factoring the difference of two squares. You're going to have two perfect squares here. The difference means subtraction. We're going to take the square root of the a square, a, the square root of the b square, b. One side will be positive and the other will be negative. So let's look at this problem. When I say factor completely, the first thing I'd like for you to do to see if we can take out a greatest common monomial factor. The greatest common monomial factor here is just a 1, so everything stays the same. Now we have to determine if these two terms are perfect squares. So we look at the square root of 81 is 9, the square root of m squared is m. The square root of 49 is 7, the square root of n squared is n. So those are perfect squares. So what we're going to do, we take the square root of 81, 9, 9. The square root of m squared, m. The square root of 49, 7, 7. The square root of n squared will be n. One sign will be positive and the other sign will be negative. And this is factoring the difference of two squares. And again, remember to go back and check it using FOIL, first, outer, and last. Next, we're going to look at factoring perfect square trinomials. And we're going to have to determine if a trinomial is a perfect square. So notice here we take the square root of the a square, a, take the square root of the b square, b. This sign is minus and both these signs are minus. And they're two identical binomials, so we have the binomial being square. The same thing for the plus sign here. Notice that these two binomials are identical, so it would be the binomial square. So let's look at some examples. And again, when I say factor completely, I want you to see if you can take out a greatest common monomial factor. But the only thing here will be a 1. So now we have to determine if this is a perfect square trinomial. So we'll look at the first term and this third term to see if they are perfect squares. The square root of 25 is 5. The square root of y squared is y. The square root of 36 is 6. So 25, y squared, and the 36 are perfect squares. Note that when I multiply the 5 times the y times the 6, I get 30y. Then if I said twice that, I get 60y. And notice, you see, it's twice the square root of like the a squared and the b squared gives us this middle term here. So that gives us that middle term, which is here. So you see, so here we've got the square root of 25, 5, the square root of y squared, y, the square root of 36, 6. Since this sign is negative, this is a perfect square trinomial, then both of these sides will be negative, and we have two identical binomials, so it's going to be this binomial square. Either one of these answers is permissible. Let's look at another factor completely. Again, we have to figure out if the first term and the third term are perfect squares, and when we take the square root of each of these terms, multiply by 2 to see if we get this middle term. So again, we take the square root of 25, which is 5, the square root of y squared, which is y, the square root of 49, which is 7, and we note that 5 times y times 7 is 35y. But if we say twice that, we get 70y, which is, you see, this middle term. And then when we factor, again, the square root of 25, 5, 5. The square root of y squared, y. Square root of 49, 7, 7. And since we have determined that this is a perfect square trinomial, both these signs have to be positive, and we have two identical binomials. So now we have the binomial square. I hope this has been a pretty good review for you. And remember, as you're watching this video, stop, rewind, review. Stop, rewind, review until you understand what's there. And thank you for viewing this video.